Good afternoon. We are going to do the notes for 7.1, ratio and proportion. Okay, so the first skill we are going to need to learn is unit analysis, which is a method of converting between units, meaning from feet to yards or pounds to ounces, those kinds of conversions. So here's the process. Number one, you prime factor the top and bottom, which is why we've worked at that already on the pre-chapter notes. Any factor over itself divides to 1, then you simplify. Step 4 is multiply the result by what we call a conversion fraction. And flip the conversion fraction to make sure that the unit cancels. What do we mean by flip it to make sure the units cancel? Well, for example, we know that there are 3 feet in 1 yard, but we can write it 2 different ways. We can also write it 1 yard over 3 feet. So the question of multiplying by the conversion fraction is, which one do we pick? Well, you pick the one that will make sure that the units cancel. And they cancel if they are top and bottom. After you've canceled the units, then you re-simplify if necessary. All right, so example 1, we're going to simplify the ratio. 4 feet to 24 inches, and the colon is read as 2. 4 feet to 24 inches. So in order to simplify it, we start by stacking it. The first one in colon form always goes on the top. The second one in colon form always goes on the bottom. All right, so simplify the ratio. We're going to prime factor the top and the bottom. So let's do that. I have 2 times 2 for the 4. And the units are just like factors. That's feet. On the bottom, 6 times 4 is 24. So 2 times 3 is 6. 2 times 2 is 24. And then I have inches. Now, we need to simplify the ratio. So to simplify the ratio, we have to remove the units. So you might add a little quick note that ratios have no units. So when we're simplifying it, we're removing the units. So we have prime factored. Now we're ready for multiply the result by a conversion fraction. Okay, you know that 1 foot is equal to 12 inches. That's your conversion. I want the feet and the inches to cancel out because this is a ratio. So I have to decide, is it feet over inches or inches over feet? You decide that by which way we'll have them cancel out. Because I have feet on top, I need the 1 foot on the bottom and the 12 inches on the top, which is 4 times 3, so 223 inches. So again, you choose which way the conversion fraction will go so that the units cancel. Well, feet and feet divide out, inches and inches divide out, and now you have something that you need to simplify. I have a 2 on bottom, 2 on top, 3 on the bottom, a 3 on top, 2 on bottom, 2 on top, 2 on bottom, 2 on top. So on the top, all I have left is a 2. On the bottom, all I have left is a 1. So the ratio is 2 to 1 in colon form. Your choice of which form to end up with, fraction or colon form, depends on how you start. This one started in colon form, so you end in colon form. This one's going to start in fraction form, so you will end in fraction form. So choose your form by what you start with. And we have reduced the ratio using a conversion fraction. Okay, let's do it again. Start by, so we're going to simplify the ratio. So we have 45 centimeters on top. We have 12 meters on the bottom. So we're going to prime factor the top and bottom. 45 is 9 times 5, so 335, and then it has centimeters. On the bottom, 12 is 4 times 3, so 223, and we have meters. Now we need to figure out what our conversion is going to be. Well, again, you know that 1 meter equals 100 centimeters. So the question is, which way do we use it? Well, we have centimeters on the top, so when we multiply by the conversion, the centimeters need to be on the bottom. So I'm going to have the 100 centimeters on the bottom, which is 10 times 10, that's the 100, and centimeters. And on the top, all I have is 1 meter. Again, we're multiplying by the conversion fraction to make this a ratio. Ratios don't have units. Okay, let's divide out what we can. 2, there are no 2's on the top. 3 will divide into 3. Meters into meters. I have a 2, but none on the top. I have a 5 on bottom, a 5 on top. I have centimeters and centimeters. And that's pretty much it. So what have I got? I have 3 times 1 on the top, which is 3. I have 4 times 2 is 8, times 10 is 80. And we're going to leave our ratio in fraction form because that's what we started with, was fraction form. All right, that's how you simplify a ratio. You have to use a conversion fraction. If you don't know the conversion fraction, Google it and get the conversion fraction. Okay, Roman numeral 2, geometric ratios. Geometric ratios are ratios that have to do with measurement. And that's, of course, going to be our focus because this is geometry. Okay, definition of a geometric ratio is a fraction, statement, or colon ratio that relates two quantities. So in a geometric ratio, the units of length must match. All forms must be completely reduced. Fraction form is always improper. And I have two ands there. You can color out the last one. So fraction form is always improper and reduced, so no mixed numbers. And the first length mentioned must go on the top of the ratio fraction. First in the colon and statement forms. So what does that mean? Okay. Let's say that we have a geometric ratio of 32 meters over 5 meters. Units of length must match. So to turn this into a geometric ratio, we divide the m's out, and that gives us 32 over 5. That is our fraction form. In colon form, the top number always goes first. It would be 32 colon 5. It means the same thing, it's just in a different form. In statement form, the first number or the top number comes first. So 32, and usually we use the word to, sometimes the word per, depending on the situation. So it's 32 to 5 meters, if we're talking about meters. So those are the three forms we're going to use. Flip the page. All right, part B, to create a ratio in fraction form. Number 1, stack the lengths in the order of the question. Number 2, convert the units if necessary using unit analysis, which we just went over. Number 3, prime factor the numbers to reduce completely. All right, let's do an example of creating a geometric ratio. The example says, a rectangle has a length of 76 inches and a width of 24 inches. Find the ratio of its length to width. Okay, length to width, to remember is the fraction bar. That means that length is going to go on top and width is going to go on bottom. We go in the same order as the statement given. Okay, so in this question, the length is 76 inches, so that goes on the top. Over the width goes 24 inches. So you can tell right away that the inches will divide out. We don't need unit analysis to make that happen. And now we reduce. 76 is 4 times 19, so 2 to 19 over 24, which is 6 times 4. So 3 times 2 for the 6, 2 times 2 for the 4. And we have a 2 that will divide to 1, another 2 that divides to 1, and we have 19 over 6. Now, if they don't specify what form they want it in, fraction form is the default form. And again, there are no mixed numbers. It is always improper but reduced. All right, let's do the other example. A triangle has a base that is 4 feet long and a height that is 30 inches high. Find the ratio of its height to its base. So our ratio is going to be height on the top over base on the bottom because that's what they said goes first. All right, so our height is 30 inches. Our base is 4 feet. And unlike the last one where we had inches and inches, this one we need to convert the units so they can divide out. Well, we know that 12 inches equals 1 foot. That's our conversion. So turning that into a fraction, I want feet to cancel. So 1 foot will go on the top of the conversion fraction. 12 inches will go on the bottom. That way, inches and inches divide out, feet and feet divide out. So what we're left with is 30, which is 6 times 5, so 2, 3, 5, over 4, which is 2 times 2, and 12, which is 6 times 2. So 2 times 3 for the 6, 2 times 2 for the, 6 times 2, not 4. So 3 times 2 times 2. There we go. All right, so I can divide a 2 out, I can divide a 3 out, and I'm left with a 5 on the top, 2, 2, 2 on the bottom, which is 8. 5 to 8 is the ratio. So sometimes you'll need a conversion fraction, sometimes you won't. It just depends on the units. Okay, so regular ratios in colon form are like, for example, A colon B is read the ratio of A to B. In colon form, it can also be shown as a fraction, which is A over B. First one goes on top, second one goes on bottom. Okay, an extended ratio, C to D to E, has a more complicated way to expand it to a fraction. So the ratio of the first two numbers is C over D. The ratio of the last two numbers is D over E, and the ratio of the first and last numbers is C over E. So the C always comes first. The left number in all three cases is on the top of the fraction. Always. The left number is always on top. So in an extended ratio, there's actually 3 ratios being shown in colon form. And that's what it breaks down to. Okay, writing proportions in fraction and colon forms. The definition of a proportion, again, is an equation stating that 2 ratios are equal. We now know there's 3 forms. There's fraction form, A over B equals C over D. We have colon form. Now this is one you haven't seen. A over B changes to A colon B. The equal sign stays where it is, and then the right fraction is C colon D. And then, of course, we have written form, which when you read this in written form, it is A is to B, that's the first fraction, as C is to D. So the equal sign in fraction form is directly transferred to the equal sign in colon form. In written form, the equal sign is the word as. A is to B as, there's the equal sign, C is to D. You need to know these three forms so that you can solve things that don't naturally come in fraction form. So for example, we're going to solve for x. It says 3 is to x as 4 is to 9. So to solve this, you need to first change it to fraction form. 3 colon x is 3 over x. 4 colon 9 is 4 over 9. And we're going to solve for x. So again, there's many ways to do this. I'm just going to keep it simple. Get a common denominator. So multiply the left by 9 over 9. Multiply the right by x over x. Now that they both have a 9x on the bottom, we can multiply both sides by 9x over 1. This will cause all the bottoms to divide out. And we have 27 equals 4x. And to get x by itself, we multiply by 1 over 4 on both sides. The 4's divide out. X is alone, and I have 27 on top and 4 on the bottom. 4 is 2 times 2. 27 is not an even number. So that is your finished answer. All right, flip the page. Using ratios to find original lengths. Okay, we're getting into more geometry-focused problems here. Show that the ratio is the same for all three sides of the triangles. When you show that the ratio is the same, you do this to prove they are similar. That's one of our geometry terms, similar. So usually the best way to do this is to identify largest side and largest side. So that is 12 over 20. Medium side and medium side. So that is 9 over 15. And then smallest side to smallest side, 3 over 5. To prove that this is that all three make the same ratio, you write the three fractions comparing their sides, prime factor and reduce the fractions, and ask yourself, do they have the same ratio? Okay, so 12 over 20. 12 is 4 times 3, so 223. 20 is 4 times 5, so 225. A 2 divides out, a 2 divides out, and we're left with 3 over 5 in its reduced form. Let's do the medium ones. 9 is 3 times 3. 15 is 3 times 5. Divide out a 3, and you have 3/5. Big sides reduced to 3/5, medium sides reduced to 3/5, smallest sides reduced to 3/5. So do they have the same ratio? The answer is yes. Therefore, they are similar triangles. Okay, let's do another example of using similarity. Here we go, example number 2. The ratio of a triangle's side lengths is 5 to 2 to 9. If the longest side length is 36 inches, how long are the other two sides? Now, first thing you need to understand is that this 5 to 2 to 9 is a ratio. That means that if you stack them into fractions, this ratio represents reduced fractions. So 5, 2, and 9 are not the actual side lengths. Just like on the one previously, 3 to 5 was not the ratio of, was not the actual side lengths of all three, except for the the lowest sides, the smallest sides. So the ratio gives you this 3/5. It does not tell you how big these two sides are. That's where we need the other piece of information, which is that the longest side length is 36 inches, and we can use that to find the other two sides. Okay, so how do you attack this? To go from reduced ratio form, which is what they gave you, back to the original side lengths, we need to know what to multiply the ratio by. This magic multiplier will be the same for all three sides. Okay, so the ratio of the sides in smallest to largest is 2 to 5 to 9. They gave us that. So we need to know what to multiply those by. We need the magic multiplier, which is m. So we need to know what 2 times m, 5 times m, and 9 times m are to get the sides. We don't know the actual side length of the smallest. We don't know the actual length of the medium. We do know that the actual length of the largest one is 36 inches because they told us that. So 9 times the magic multiplier has to be 36 inches. So we're going to write an equation from the matching pair that we have. So 9 times m, 9 times the magic multiplier has to be 36, and solve for m, our magic multiplier has to be 4 because 9 times 4 is 36. Once you have the magic multiplier, now you can use the magic multiplier to calculate the other two sides. So for the small side, it was 2 times the magic multiplier. The medium side is 5 times the magic multiplier. So filling in the magic multiplier, I have 2 times 4, which is 8 inches for the smallest side, 5 times 4, which is 20 inches for the medium side. So our triangle has side lengths 8 inches, 20 inches, and 36 inches. That is the answer. So the setup you want to pay the most attention to is this one right here. This is your work. This is what you show, and this is what you need to write to figure it out. All right, flip the page. Last page today. Example 3. A triangle's angle measures are in the extended ratio of 1 to 4 to 5. Find the measure of the angles. So 1 to 4 to 5, that's our ratio. So to find the actual sides, I need my magic multiplier. So 1 times m, 4 times m, 5 times m. All right, since we don't have a pair of matching numbers like the last one, we need a relationship. I'm sorry that space is so small. We need a relationship between the angles. Well, if it's a triangle, then we have triangle sum theorem that says all of the angles have to add up to 180. So whatever angle 1 is, plus angle 2, plus angle 3 has to be 180 degrees. If we use our side ratios, angle ratios, these are angle measures. If we use our angle measures, small, medium, large, angle 1 would be 1m, plus angle 2, which is 4m, plus angle 3, which is 5m. All three of those angles have to be added up to 180. The cool part is that is a solvable equation. 5 plus 4 plus 1 is 10m equals 180 degrees. So m equals 18. That's our magic multiplier. So now we can actually find the angles to our triangle. The angles, remember, are 1 times m, 4 times m, 5 times m. So we have 1 times 18, 4 times 18, 5 times 18 for the actual angles. That gives us 18 degrees, 72 degrees, 90 degrees. That's our answer. So what makes this one different than the last problem is this ratio were angle measures, and they didn't give us an actual measure of one of the angles. If they did, we could use the same technique that we used in example 2 and use the angle measure they gave us to figure out the magic multiplier. Since they didn't, however, we had to use a different relationship, and angles do have a special relationship in that if they're in a triangle, they add up to 180. So that relationship was how we got to our magic multiplier. All right, and use your magic multiplier to find the 3 angle measures. Some of your problems on your homework are going to show you fractions instead of, or sorry, not fractions, I mean triangles instead of angle measurements, but it's basically the same process whether it's triangles or just the measurements. All right, that is the end of the notes. Have a good rest of your day.